All right, for this first one, as we can see, we have that the annual, the mean annual temperature for Earth recorded at 50-year intervals are shown in the table. So these temperatures are all mean annual temperatures, and as we can see the 50-year interval, here you have plus 50, here you have plus 50, etc. Okay? How do you read this? Well, I don't know. In 1908, the mean annual temperature was 9.13 Celsius. All right, so that is like the context. And then our good old friend Tami creates a linear model for this data by finding the equation of the straight line passing through the points with coordinates blah and blah. Okay, so they are using this point and this point. We need to calculate the gradient of the straight line that passes through these 2 points. Now, first things first, a little bit of context. So notice that they find the equation of the straight line passing through those 2 points. See? And notice how the temperature goes changing. For example, from here to here, it went down. It went down just around 0.12. Then it went up plus 0.02. Here it went up plus 0.01. If it was a straight line, all of these numbers would be the same, but they're not. And so let's really understand what Tami is doing. Technically, if you take, like, I don't know, if you draw that graph, right? And here you have, actually, let's make it like this. So let's say that here you have temperature, and here you have time. There's a bunch of dots in between, right? And technically, there's a curve going along it. See? And so what Tami is doing by taking a straight line of 2 points is that we are calculating this straight line. Okay? We're calculating that straight line. We're ignoring the parts with a curve. We're actually not making a curve. We're making a straight line. So just so that we understand a little bit the context and what's going on. Okay? All right, enough blah blah. For part A, they ask us to calculate the gradient, what the fuck is that, of the straight line that passes through these 2 points. And so gradient, and actually let me pull something up over here. So for gradient, we have the famous formula booklet. A good thing to have in mind, you guys, is that the day of the test, you're walking in with just a couple things. You're walking in with a pen and pencil. You're walking in with all the motivation in your brain. You're walking in with 2 years of studying the IB, and you're also walking in with 2 hours of sleep. You're walking in with your graphing calculator and the formula booklet. Guys, these last two, the formula booklet and the graphing calculator, are tools. Okay, they are tools that will be available the day of the test. So it's important to get familiar with your tools so that the day of the test you can use them. Okay, and so why do I say this? Because you might be reading this, you read the word gradient, and you're like, fuck, I don't remember exactly what it is, but I know it's in the formula booklet. So you open up your formula booklet, you go to wherever it says gradient, there it is. And this helps you refresh your memory a little bit. So what the heck is gradient? Well, this is in the context, or it's in the same block, right? It's in the same block as equations of a straight line. Ah, okay, so this m is also this m, and also this m. Okay, and now it makes a little bit more sense. Okay, so here up top we have technically how y changes, and on the bottom we have technically how x changes. Ah, okay, so this is slope. This is slope. And as some of you might have heard, well, how does y change? How does it rise? How does x change? The horizontal one, how does it run? Some people have heard of rise over run. Some people just hear of slope. Some people hear about change of y and change in x, rate of change. There's a lot of different ways to say this. What am I trying to express? Gradient is the same as slope. Okay, so it's how your line changes. See, for example, a line that looks like this, let's say this has a slope of 1. Well, something that goes like that will have a slope of -1. See? And something that it grows faster will have a greater slope, right? So like m equals, I don't know, 10, and something that grows like slower, but in the negative side, would be a slope of, I don't know, negative 20, okay? So that is slope, that is straight lines. Let's get to it. See, so the gradient formula, as we can see here, is y2 minus y1 divided by x2 minus x1. So m equals this. Okay, so what the heck is y2? What is y1? What is x2? What is x1? I got you. Relax. So x2 and x1 and all this shit is just expressing a point. Okay? Chill out. For example, point 1 or whatever. Point is x1 goes with y1. x2 goes with y2. Okay, this is just expressing a point on your graph, okay? For example, you might pick, honestly, you might pick that this is your x1, y1. So x would be here. I mean, x1 would be here, y1 would be here. See? Or you might pick for this guy to be y2 and x2. So this point here would be x2, y2. Okay, it's literally just points on your line. See? And so here I have 2 points. See? And you might be thinking, damn, which is the first one? Which is the second one? Dude, as long as you're consistent, it's going to work. See? So let's do it the most intuitive way possible. The first one that shows up is going to be x1, y1. The second one that shows up is going to be x2, y2. And so I go ahead and plug in. So y2 is 9.45 minus y1, which is 8.73. All of this divided by x2, which is 1958, minus 1708, x1. So trust the process. Here's the formula, no worries. I plug that into my calculator. There's an easy way to plug it into my calculator, okay? Because I have a fraction, you can press alpha and then y equals. Alpha y equals, you hit that F1 button, brings up this menu. There's a lot of stuff on it, but it's just fractions. The first one is a fraction. So here you can put 9.45 minus 8.73, 1958. This is just a calculator trick to get it faster, okay? That's all. You end up with 0.00288. What might have happened to you is that you got the answer in a fraction, okay? You might have gotten it in the answer of 9 divided by 325. See? You might have gotten it like this, and you're like, damn, why don't I have the decimal? Well, if you don't have the decimal, you can find it like this. And so in one hand, you have it expressed as a fraction. In the other hand, you have it expressed as a decimal. It's the same number, okay? Actually, you can leave your answer as a fraction. Let me just show you the answer key real quick. You can leave it in either of the two ways. See? I'm just saying, like, if your calculator is giving it to you in fraction and you're freaking out, just don't freak out. It's all right. It's normal. And if you want it in decimal, well, just write it again, but with a division symbol. See? All right, whatever. Part A, M for part A is going to be, as we said, 0.00288. So let me just go like this, leave it nice and pretty, and check. For part B, part I, we need to interpret the meaning of the gradient in the context of the question. All right, so technically, the gradient, as we said, is a little bit like rate of change. See, here I mentioned the rate of change. And so, this slope is how x relates to y. See, it's a way to interpret how x relates to y. And in the context of the question, I have year on x, year on my x, and temperature for y. And so a slope of 0.00288 means that as the years go by, temperature increases. And that's it. Okay, so technically the gradient would be the yearly change in temperature. And notice, you're always going to be expressing like whatever x is. So technically, like the original definition, I should have started here. The original definition is kind of like um, the change in x causing a change in y. And so what is x in this context? It is time, it is years. See? And so the change in x causing a change in y, the, the change in years causing a change in temperature. All right, this is like the very intuitive way to put it. And let's recall that here they talk about the mean annual temperature. And so, oh, and also we talk about mean annual temperature. And so technically, if you want to get a little bit fancier with this, you can say the yearly change, right? The mean yearly change in mean annual temperature. Why annual? Because we have annual temperatures up there. See? All right, so I just want to show a little bit more intuitively. You're always going to be expressing x and then y. X was years, y was temperature, right? X is years, y was temperature. And then we plug in the buzzwords that they said, mean yearly, right? Mean annual. So that is just a very more thorough way to put it. All right, whatever. That is for part I. For part double I, we need to state appropriate units for the gradient. All right, so again, part B is like a full-on context question. See? And so what units am I working with? Well, we already noticed earlier that we have mean annual temperatures. But in what? In Fahrenheit? In Celsius. Okay, so we're going to be talking about Celsius. Every how much time? Ah, every year. All right, let's boil this down a little bit. See, so from top to bottom, what do we start off with? We start off with, we are talking about temperature per time. Temperature per time. And which temperature are we talking about? We're talking about Celsius. So Celsius, I don't think I'm writing that correctly, but I don't care. Celsius, and how much time? Year. And so this allows you, and this is the answer key actually, you can talk about Celsius per year. Another way you can express it, in case it makes you feel a little bit more comfortable, you can talk about degrees Celsius per year. Okay? Both of these last two are in the answer key, trust me. Find your way to express it. Okay? Whatever floats your boat. But start from the intuition. In general, we're talking about temperature and time. Which temperature? Celsius. Which time? Per year. Appropriate units for the gradient? Celsius per year. That is for part B. A small comment I would like to make. See? Part B, usually, and in some of my videos I talk about this a lot, what you need in part B is something you needed in part A, right? But this is an excellent example of that not being the case. And you might be telling me, well, why does that help me? It helps you because the day of tomorrow, you might be mega stuck on part A, but you realize, yo, part B doesn't need anything from part A. Actually, part B is a context question. So what does that mean? Maybe you're running low on time. Maybe it's near the end of the time of your test and like whatever, you're like freaking out or whatever, like, oh, where can I get points? Part B is a context question. It doesn't need anything from any of the other parts. Interpret the meaning of the gradient. It's not telling you to get the gradient. It's telling you to interpret the meaning of the gradient. So I'm just pointing that out, that part B can do it without part A. It's good to notice when it's the case to earn some free points if you're running low on time and stuff like that. That's the only reason I'm pointing it out. Now, The IB being the IB, for part C, we need to find the equation of the line giving your answer in the form y equals mx plus c. Notice how we need m. And what is m? M is gradient. So in this case, part C needs something from part A. Interesting. Why is this worth knowing? Because it's a hint of what you might need to do or the path you need to take if you realize that if you realize that part C needs something from part A. Usually it's that part C needs something from part B, but part B is a context question. I mean, guys, this could have been like the last one. It could have been like H or whatever. And that wouldn't change anything in your process. It doesn't change your process. It helps you understand better, yes, but it doesn't change your process. So it's good to notice which parts need each other, which parts don't need each other, and use that itself as a hint. So I just added a tool to your toolbox. I hope it helps. Whatever, part C, find the equation. So it is asking us to give it in the form y equals mx plus c. And yes, it's true, you can get there like pretty quickly just by plugging in. But let me give you the more conservative approach. So when we look at the equation of a straight line, y equals mx plus c is right here. Okay? Now there are two other ways to express the same thing. You have this one in green. Well, let's put them all in green. So you have that one in green, this other one in green, and this last one in green. Guys, you really need to understand the following. These three equations are the same thing. They're the same thing, just like moved around a little bit. Okay? And so you can start in any of these and reach any of the other forms. Now, what usually happens? What usually happens is that the one in the middle, no one cares about unless they ask you to answer in that form. Honestly, no one cares about this one unless they ask you to answer in this form. What usually happens is that you go from this one over to that one, or from this one over to they ask you to answer in this form. Okay? Why do I urge you to start from this one? Because this one is usually all you need in order to create the equation of a line. Why? Because this one on the right side, well, what does it ask for? It asks for m, so you need m, and it asks for x1, y1, which is a set of points. Usually, you guys, finding a set of points and finding m is not that hard. Okay, it's super doable. You can do it. See? On the other hand, this one on the left side, what does it ask for? It also asks for m, so that's something that they have in common, and it asks for c. Now, c is the y-intercept. And so, do I have the y-intercept of my equation up here? No. Is there a way I can get it using the equation on the left? Yes. Is it intuitive? No. Which is the most intuitive option? The one on the right side. So fuck you, we're using the one on the right. So the one on the right, we're gonna get to this form eventually. Okay, so trust the process. Just get used to using the one on the right because it's the most friendly option. Okay, so let me make some space down here. Da, 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 da. As I said, my equation is, from the formula booklet, y minus y1 equals m parentheses x minus x1. Okay, so which point am I going to use? Doesn't matter. You pick. I'm going to use this one. You can use the other one. I don't care. So we know that m is, actually, let's go piece by piece. So y1, we're saying is 8.73. Cool. 8.73. M is 0.00288. 0.00288. Parentheses x minus x1. 1708. Cool. Notice how I didn't plug anything in for x and y. See? That's fine. Relax. Don't worry. If you notice this form over here, y and x is also going to remain unchanged, but you will plug in for m and you will plug in for c. How do you get c from here? Just trust the process. Okay, trust the process. Get this line. Find your way to reach y equals mx plus c. Okay? Go from this to that. go from this to that. That is our goal. Trust the process. If you learn all these different processes, you're for sure going to get a 4 and probably a 5. Okay, learn the intuition of the problems, learn the procedure, learn the method. That is the most important part. Learn the method. So you make an equation of a straight line. Start with this guy. It's the most friendly one. And then reach everything else. See? All right, what do I do from here? What I suggest is first deal with this parentheses. So multiply here, multiply here. So y minus 8.73 equals 0.00288x minus whatever that number is we're about to find out. So 0.00288 times negative 1708. There it is, minus 4.91904. Okay, so get y alone. See? Get y alone. Y is not alone. It is being affected by minus 8.73. So we're going to add. We're going to add 8.73. This goes away with this. Plus 8.73 on this side. So I end up with y equals 0.00288x plus something. So this plus this. Lo and behold, plus 3.81096. Does this look familiar, you guys? It damn better look familiar because this is just the same as y equals mx plus c. Ah, okay. So what's my y-intercept? My y-intercept is 3.81096. And my slope, well, my slope is right here. My slope, 0.00288 is my m, which is what I got over here. Wow, this is magical. No, it's not magical. It's called knowing the procedure and always starting from this one. See? Technically, if any of you noticed, I'm just going to show it quickly. You can use the one on the left. I'm not going to do the whole process, but you can figure it out yourself. So the one on the left is y equals mx plus c. And technically, because you already know m, you can plug in m. So it's 0.00288x plus c. And here you can also plug in a set of points. You can plug in x, you can plug in y. And so same thing, you can plug in y, so 8.73 equals 0.00288 times x, which is 1708, plus c. And so this can give you c. And now that I'm doing it, fuck it, I'm just going to show you. So 0.00288 times 1708. Yeah, that gives you that number. So 8.73 equals 4.91904 plus c. So c has to be 8.73 minus this other guy. So c has to be 3.81096, which is the same c that I got over there. And so then you can plug this back in over there, and you end up with y equals 0.00288 x plus 3.81096. I know some of you might be thinking, okay, you just showed me two ways, and it was way faster than one on the left. And I'm like, yes, it's true, but I think way more intuitively is this guy. Okay, I think it's more intuitive. Getting the y-intercept can be a little bit weird to plug in x and y. I know for some people they're like, huh? Because it is weird. This is the weird but fast way. This is the conservative, a little bit longer, but reliable way. All right. Find what works for you. I'm just showing you the tools. I suggest the old reliable. See? To each their own, whatever. So for part C, well, we did it. See? So for part C, the equation is, just to write it down, y equals 0.00288x plus 3.81096. Yeah, then for part D, we need to use Tami's model to estimate the mean annual temperature in the year 2000. All right, so the main idea we have to capitalize on is we are estimating what thing? We estimate the mean annual temperature. Okay, what is mean annual temperature? Mean annual temperature is, it's my y. So we're estimating a y in the year 2000. The year 2000, what is it? It's x. Okay, so if they tell me year 2000, that means x equals 2000. And so we're going to plug in x and figure out my y. Pretty simple, right? So I plug in 2000 for my x and figure out my y. 96. Just so that we're all on the same page here, technically what I'm doing when I plug in 2000 here is what is y when x is 2000? Okay, that is all I'm doing. What is y when x is 2000? Which in the context of the problem is what is the temperature when the year is 2000? Now, of course, this is an estimate because Tami's model is trying to estimate, right? But this is the context, see? You ask the function, what is y when x is 2000? That is all you're doing. So plug into your calculator. Let's see what happens. 0.00288 times 2000 plus 3.81096. Correcto. There it is. And so technically you can write that the answer is 9.57096. Put the units, Celsius. If you want to do it to three significant figures, you can count 1, 2, 3. Do you round this one up or down? You keep it the same, so it stays as 9.57 Celsius. That is for part D. Again, not that hard, but really understand the context of what you're doing. You're asking the function, what is y when x is 2000? Y is temperature, x is year 2000. Then we have our buddy Thandizo use a linear regression to obtain a model for the data. And so for part I, we need to find the equation of the regression line y on x. So remember how I said earlier that technically this graph, I don't know, looks probably something like this, right? And you have like a curve, right? So here's the thing. What Tami did, all right, from parts A to D, what Tami did was find the equation, I don't know, like from here to here. See, the straight line from there to there. Okay? And what Thandizo is going to try to do is that he's going to take all these different points, everything in between. He's going to take all these different points and find what we call the regression line. Okay? And just very, very intuitively, the regression line is just sort of like the average of all these points. See? So the average of all these points, if you draw a line, would probably be something that cuts like that. Okay, so it's a little bit different than Tami's line, but that's the main idea. See? For example, if you have, I don't know, like a scatter plot that looks something like this, and it's sort of aiming upwards, the regression line would probably look something like that. See? If you have a scatter plot with a bunch of stuff sort of like aiming down, then yeah, I mean, your regression line might be a little bit off, but it's going to be like aiming down a little bit. See? So that is what the regression line does. That's why it's useful. It can help you estimate, which we actually do later. But we will see that in a second. See? So the equation of the regression line, y on x. We understand what they're asking for, but maybe we don't know how to do it yet. See? And here is where, remember how I mentioned in part A, that you gotta get used to or get familiar with the formula booklet because it's one of the tools you're gonna be using. Well, there are two main things you gotta get used to. No sleep. The formula booklet, it's actually three things. And the graphing calculator. See, get familiar with it. There's a lot of tools in there. See, and so the idea is that the moment you read the word regression, you immediately think that is in my calculator. Maybe you're not sure where, maybe you don't recall exactly its location, but you know it's in there. You know that shit is in there. So you pull out your calculator and you're like, damn, this guy on YouTube said it's in here. I know it's in here. I've used it before. where the hell is it? And you're gonna start, you're gonna start looking everywhere, like here, there, blah, blah, blah. Like, okay, go piece by piece. This is a regression line. You're trying to estimate something. You have a linear model. So, you're estimating stuff. Okay, you are in the world of statistics. So, kapow, you press the stat button. Okay, so I can edit, I can calculate. There are tests. Eventually, you're going to find that in the calculate tab, down here you have line reg. Notice how it says line reg ax plus b. So it's literally a linear regression of a straight line. Ax plus b makes reference to the famous y equals mx plus c. Okay? So, you press linear reg, see what it asks for. What does it ask for? It asks for an x list, it asks for a y list, the frequency list only if it's necessary, and you can store your regression equation in one of your y equals. Oops, that was not what I meant to do. Although that looks really cool. Damn. And you can store your reg EQ if you want to. See? In one of your y equals. For example, you want to store it in, I don't know, y2. It's going to show up in your y equals on y2. See? How did I just do that? I pressed alpha, trace, and hit F4. See? I don't think you're ever going to really want to do this, but you can. That's all I'm saying. See? All right. Whatever. So, we find line reg. We see what it asks for. We need the lists. See? Where did I change the lists? I forgot. Go to stat, edit. You want to edit your lists. Go stat, go edit. Boom, there it is. See? You probably have a bunch of stuff from another exercise. That's cool. Go ahead and clear those lists. See? A quick way to do it is go up top on the title L1, clear, enter. Clear, enter. Cleans it up right away. Nice and easy. So, as we said or noticed in line reg, L1 is X. L1 is X and Y is L2. Okay, so which one is X in this context? X is literally year. See? So we're going to put all my years on my L1. 1708, 1758, 1808, 1858, 1908, 1958, and 2008. Take a second, check your work. It's always worth it. So this is fine, 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 fine and dandy. All this beautiful in the world. Cool. So that is X. Now we put in my Y values, which is temperature, my Y, my X, my L2. So 8.73, 9.22. Oh, small mistake. Happens to anyone. Beautiful. 8.73, 9.22, 9.10, 9.12, 9.13, blah, 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 blah. All right, cool. So now that we plugged everything in and we double checked and everything is nice and dandy, we can go back to the line reg thing. See, so if I go to line reg, well, I have my X list, I have my Y list, and I'm going to store my equation just because I want to. See, whatever. I'm going to put it in Y1. This is unnecessary, but it's cool to do it. See, there is no frequency list. If you had a frequency list, you would put something here, but I don't. So unless they give you a frequency list, you should just never worry about this, okay? Go ahead and press calculate. Boom, there it is. See? So it's telling you that for the equation of y equals ax plus b, which is the same as y equals mx plus c, ¿vale? Your a, which is your slope, is going to be 0.0025, and your y-intercept is going to be around 4.4. Okay, cool. So for my answer, I can write y equals 0.00256. Yeah, let's leave it at 256. Three significant figures. You count 1, 2, 3. This fifth one to the right. Round it up. Blah, blah, blah. X plus the y-intercept, which is count 1, 2, 3. This 6. Do you round it up or down? You leave it as 6. Okay. 4.46. So here is part E, part I. See? Cool. Then they tell you to find the value of R, the Pearson's product moment correlation coefficient. What the fuck did I just read? You need to find R. Let me just erase this for a sec. You need to find R, the Pearson's product moment correlation coefficient. Okay, this is probably the biggest buzzword that you're gonna have to learn. Okay, the biggest vocab word that should jump out to you and be like, whoa, if I see this, that means I need to do that. See? So the value of R helps you understand a little bit how your how your linear regression relates to your data. For example, this line in orange, okay, probably has an R like near 1. See? It's very aligned with my data, and an R value of 1 means that it's like it cuts through your data very closely. It's a good estimator, like it correlates well. See, there's a correlation. What is correlation? Well, as x increases, so does y. See? And so something that can be correlated is like, dude, I don't know. Amount of sunlight the plant has and its height. And so the more sunlight it has, the higher it gets. It kind of makes sense, right? Or I don't know, like just whatever. See? Correlation, there's a lot of examples, I'm sure you can find them. R helps you identify how strong that correlation is. And so a correlation of, I don't know, maybe like near 0, so near 0 would be like a line that's something like this. Maybe your data is all over the place, right? It's all over the place. It wasn't able to do a good correlation. An R near 0 would look like that. See? There is no correlation between your data. Everything's just kind of random. See? Yeah. Whatever. So that's the idea of R. Pearson's product moment correlation coefficient. Yeah. Sounds fancy as fuck, but it's just correlation. So you stick to that. It's just correlation. And so your calculator should be giving you the R value when you do line reg. Okay? In fact, some of you probably already have it, and they're like, why does yours not show up, dude? You're like a fucking loser. Why doesn't it show up? Well, it's not that you're a loser, it's that your calculator does what it asks, does what it is asked to do perfectly. Sometimes too perfectly. See? If you don't put in that extra parentheses, or you don't ask for it to give you R, it's not going to give you R. It just doesn't care. For some of you, it shows up because you already put the setting beforehand, but for those of you that it doesn't, you have to go to mode. Okay, this button next to the blue one, mode. And here there's a bunch of stuff that you should always keep the same. And one of them down here is stat diagnostics. Don't keep it off, keep it on. Why? Because now the next time you do line reg, keeping everything the same, kapow! You get extra information and there is your R value. Your R value is going to be 8, sorry, it's going to be 0.861 significant figures. See? There's your R value. See? And so notice how part E really, you just needed to be good with the calculator. It wasn't being like savvy at math and good at this or that and knowing all these math tricks. Nah, dude. It was just knowing what your calculator has, knowing its capabilities, and knowing where to find it. That's it. I insist, you guys. A big part of this course, in my opinion, is just managing the graphing calculator. Straight up. For almost all of these statistics parts, it's just knowing the tools that you have and knowing what they do. So get used to it, practice it, get familiar with the formula booklet as well. See? The day of the test, no sleep, formula booklet, graphing calculator, and a couple other things. See? But the main things are these. These are the main tools you're going to use and have, so practice with these. Do your homework with these. Love them, because they're going to save your ass the day of the test. All right, that is part E. See? Part F, we have that we need to use Thandizo's model to estimate the mean annual temperature in the year 2000. So notice how this is pretty much the same as part D, just that now we're using Thandizo's model. So, again, same thing. X equals 2000 because we're talking about the year 2000. And we need to estimate the mean annual temperature. What was temperature? Temperature was y. So we need to find the y when x is 2000. This is literally the same as part D, just that with the new equation. What is the equation that we're using now? It is right there. So we're going to be putting 2000 into that. See? This will look better. So we have 0.00256 times the famous 2000 plus 4.46. There it is, you guys. There it is. For part F, we have that the mean temperature for the year 2000, according to Thandizo's model, is 9.58 Celsius. All right, so Tami's model and Thandizo's model were incredibly close. I mean, Tami's is 9.57, Thandizo's is 9.58. I don't know which one is better. It's not part of the question, but it's cool to think about, right? Which one ended up being more accurate? I don't know. Anyways, then they tell us that Thandizo uses his regression line to predict the year when the mean annual temperature will first exceed 15 Celsius. So we need to state two reasons why Thandizo's prediction may not be valid. Alright, and this part is a little more theoretical, it's a little bit more intuitive actually, and we need to talk about why a regression line might suck at predicting. Why would a regression line suck at predicting? On the one hand, you have this thing that they call, and this should come to mind immediately, at least in the future, this thing called extrapolation. And so extrapolation is a little bit like the, let me explain it another way. See, so extrapolation is a little bit like, let me make some space for my homies. Yeah. Extrapolation is a little bit like you have your graph over here. See? And let's say, oh, here's a good one. So here you have test score, and here you have time studying. And so according to this, the graph would probably look something like, it's probably gonna grow like really fast, right? It's probably gonna be something like that. Like the more you study, the better it's gonna go for you. See, so probably something like this. See? Yeah. If you use extrapolation here, you would conclude like, oh, eventually, like, eventually, I'm gonna score 1,000%. Guys, does it make sense to score 1,000%? Nah, dude. Your maximum is 100%. And so extrapolation, what it kind of does, that sometimes it's right, sometimes it's wrong, is that it takes a picture here and it says, okay, how would the picture look if it was bigger? See? And sometimes it doesn't make much sense to reach 1,000%. See? And much like over here, you see how the temperatures are slowly growing. Well, when you extrapolate, you're assuming they're going to keep growing like this always, right? But how much will it get to grow, right? How much, what is the limit? We don't know. Now, I don't want to get like all, like polemic or whatever. Like we're talking about global warming basically. But stat from the angle of statistics, in just this exercise, okay, this is not like mega professional or anything, but in just this exercise, it's hard to extrapolate so far out. Okay, that's the whole point. These temperatures are around 8 or 9. And you're trying to extrapolate, like all these years, around 8 or 9 or 10. See? It doesn't even reach 10, but it's close to 10. See, it's around 8 or 9 or 10, and you're trying to extrapolate all the way to 15. Okay, that is way out. It is way different than the data you have at hand. And so, one argument for why the regression line might suck at predicting or not be valid, one of them is extrapolation. You literally just put the word extrapolation, and they're going to get it. In fact, in your answer key, it says just extrapolation. You put the word extrapolation, boom, you get a point. Easy as that. See? So, on the one hand, you have extrapolation, which for a regression line, it's just, it can make it not valid. See? It might be, it might not be, it can make it not valid. It is a reason. All right, on the one hand, we have that. See? The other reason is a little harder. See? Let me tell you why. Notice for part F, when we used Thandizo's model to estimate the mean annual temperature in the year 2000, we were plugging in an x. We were plugging in an x in order to get a y. In part D, we were again plugging in an x in order to get a y. And over here in part G, technically they're asking us to plug in a y and get an x. And regression lines, this is just like a mathy thing, but regression lines are good at doing it the other way around. They're good at finding y through an x. They're not as good as finding x through a y. It's not that they can't, it's just that they're not as good. And so, the other reason you're going to be putting, and over here I have a fucking mess, so I'm just going to show you the answer key, but you guys got the idea, which is what matters. On the one hand, we have extrapolation. On the other hand, is that you cannot, at least not always reliably, make a prediction of x from a value of y. So, in other words, it's what I mentioned. If you plug in y equals 15 Celsius, in order to get an x, it's not as reliable as plugging in 2000 for x and trying to get a y. Okay, and this is just the nature of math. It's easier to get your dependent variable through your independent one. See? It's easier to plug in x and get a y than through the y get an x. See? Another way I can sort of make this reach you if you're still like, what the hell, what's going on? We talk a lot about how a function is like a box. See? It's like a machine. It's like you plug in an x into your function. Here's the black box. And you get a y value. See? You're supposed to plug in x and get a y. And so doing it the other way around, the box was not really made for that. Does it work? Yeah, it can work, but, and here's the main point, it's not always reliable to do that. You might encounter some problems that I'm not going to get into because this video is probably way too long already, but it's not always reliable. It's not what you're supposed to do. The main idea here and the main thing you have to notice is that you are trying to find x through a y. That should ring a big red flag. Ladies and gentlemen, that is G, and that is for number 1.